So let's see where we are with projectile motion now. We started with a ball rolling off a table. We were able to find the range because we knew the horizontal velocity remained constant. The force of gravity is what pulled it down. And we used the height to get the time for the horizontal motion and got the range. I call this a level 1 problem. Then we saw what happened when a ball was launched from the ground and it landed back on the ground. The y component is the reason why it went up. Gravity pulled it back down. And the x component carried it over. The entire time it's in the air, the horizontal velocity still remained constant. The time was found from the vertical motion. We used our kinematics to find the time up, double the time up, because that's the same as the time down, and we could find the range. This is what I would call a level 2 problem. And then we moved on to something harder, where the ball was launched at an angle and from a height. We split the problem up into 2 parts to find the time up and the time down, which is now longer than the time up. Together, they're the time of flight, and then we had the horizontal velocity times that time to give us the range. This I consider a level 3 problem. The time up is found the same way we did here, using that initial velocity in the y direction. The time down is the same way we did here, finding the time it takes to fall that distance. So you can see a level 3 is like a combination of a level 2 and a level 1, but there's something that's in common in all of them. The range is the Vx times t. And now let's review our graphing motion concepts. X will represent the position in the x direction. We're moving at a constant velocity horizontally. So as time goes on, the ball moves forward. In another equal interval of time, it will travel an equal distance. We get a straight diagonal line. The velocity in the x direction, that's constant. And that means the slope of this line gets graphed here. Acceleration in the x direction, well, there is no force horizontally, so that acceleration is 0 for the whole trip. That agrees with this horizontal slope. Now, what about the y position? If the height of the floor is 0, then this must be a positive height. So we start up high. And a little while later, we've dropped a little bit. And then a little while later, we've dropped further because it's accelerating downward. In the last time interval, it will fall even further. The slope of the line at the beginning should be 0, representing 0 initial vertical velocity. The velocity in the y direction versus time starts out at 0 vertical velocity. Look at the diagram. The velocity is horizontal. There is no vertical component. Now you can look at the slope of this curve, and it's getting steeper and steeper negative, which would generate a velocity that's becoming more and more negative here. And you can just look at the y component over here. It's going to be falling faster and faster. And the acceleration versus time in the y direction, that of course has to be negative 9.8, which would agree with the negative slope of this curve. There's nothing new here in graphing motion for projectile motion. It's just that we're doing it in one dimension and then a second dimension. Well, how about a level 2 problem? We have the ball launched at an angle, and we have an x and a y component. What does the x position look like? It's going to move an equal distance in equal time intervals because the horizontal velocity remains constant. We're still going to get the same diagonal line. We're still going to get a horizontal line on the velocity in the x direction. And there'll be no acceleration in the x direction. Now the motion in the y direction. Do the first point. You're starting off at a height of 0, so we start here. In a little bit of time, we've gone up quite a bit. In the same amount of time, we haven't gone up as far because we're slowing down. In another interval of time, we only go up a little bit because we've come to a stop now. Of course, the ball returns back down to 0 height at the end of the trajectory. We get the curve. Now, what about the initial velocity in the y direction? We have a vertical component. That's positive. We put the first point here. That agrees with the positive initial slope in the position versus time graph. At some point, we reach zero velocity. And then when we come down to the ground, we have a steep negative slope, giving us a negative velocity. This just tells me that we started with the ball going up, and it kept slowing down until we got to the top, and then it sped up coming down till we get back to the bottom. Now, what about the acceleration in the y direction? That's still the same at negative 9.8 meters per second squared, which agrees with the negative slope of this line. And now for a level 3 problem. Still get that straight diagonal line, the horizontal velocity line, and no acceleration in the x direction still. And now for the vertical motion. We start off above the floor. So we put a point above zero height, but we're going up. So after a little while, we reach the top, the highest point. In this same amount of time, we're back to where we started from vertically. But we still have to fall back to the floor, generating this curve. This has to have a positive slope to represent the positive vertical initial velocity. So we start with that value for the initial vertical velocity. At this time, we reach zero velocity vertically. Now we're falling a greater distance down to the floor, which will give us time to speed up a greater value negatively. So we have a more negative value for the velocity at the end than a positive initial velocity here. And of course, it's negative 9.8 meters per second squared vertically the whole way across, which matches that slope. Well, here we have a plane flying horizontally at height h. It's going to drop a care package to this target. So how far from the target should the plane drop the package? It's a projectile motion problem. That's what these word problems are going to be like. You might not recognize them at first, but draw a diagram. You see what's going to happen? It's the same thing as asking what's the range. Let's say the velocity was 125 meters per second, and it's going to be flying 200 meters above the ground. Just use 1/2 gt squared, 200 meters. The time to drop is 6.39 seconds. The whole time it's falling, it's moving at a constant horizontal velocity. So we take the 6.39 seconds times 125 meters per second, and we get 798.6 meters. So the pilot needs to know to drop the package almost 800 meters before the plane gets to the target. So what does the pilot see the package doing? As the package falls, the plane is moving horizontally at the same speed as the package is. The pilot sees the package falling under the plane. Okay, in real life, that package is going to drift behind the plane because of air resistance. We're ignoring air resistance. Let's again try this problem. 15 meters per second, launched from the ground, 30 degrees. What's the range? Of course, you'll break it up into components, 12.99 meters per second x, 7.5 meters per second y. Time up, v initial, divided by g. That's the y velocity. We get 0.7653 seconds on the way up, and that's the same time on the way down. Horizontal velocity times the total time of flight, and we get a range of 19.88 meters. Now let's see what we get if I change the angle. We'll make it 60 degrees, but we'll still launch at the same speed of 15 meters per second. If you recognize the geometry here, we're going to put the 12.99 meters per second vertically, and now horizontally, we have 7.5 meters per second. And we get 1.3255 seconds on the way up. That's the same as on the way down. And so double that gives us a time of flight of 2.6510 seconds times the horizontal velocity, which is now 7.5 meters per second. And my goodness, I get the same range. How did that happen? What, any angle gives us the same range? Hardly. It's just that the x and y components have been reversed. In the low angle, we had a large x component, which got us sideways pretty quickly, but we didn't have a lot of hang time because the y velocity was small. In the next problem, we had a smaller x velocity, took longer to get out here, but we had plenty of time because we had a bigger y velocity. Here's a football application for this situation. What if a punter was going to punt the ball and his team had to get down here to go tackle the receiver? Would you want him to kick it at 30 degrees or at 60 degrees? It's going to be the same range either way. Well, obviously, you want to do it at 60 degrees because it's going to take longer for the ball to get there, giving your guys more time to get down there. So this is what they talk about with hang time when a punter punts the ball. Let's look at the math in more general terms. The range is the horizontal velocity times time, and the horizontal velocity can be found from the launch velocity and the angle. Now we can take v cosine theta times time of flight. And we know the initial velocity in the y direction can be found from v sine theta, which allows us to find the time up. I can replace vyi with v sine theta, and then just multiply this by 2 to get the time up and time down, the total time. And that's 2 times time up. Now maybe you can look at the formula and see under the circumstances at which we get the same range. If I just switch the x and y components of the velocity, I'll still get the same range. It won't make any difference if I do v cosine theta times v sine theta or v sine theta times v cosine theta. And that's what you're doing when you're switching these components around. So if we launch at 10 degrees or 80 degrees, we get the same range. In other words, complementary angles will give you the same range. So what angle should we launch to get the maximum range? This is Vx, that's Vy. If we want to get the maximum range, we need to maximize this quantity and that quantity simultaneously. If I make this too big, that'll be too small. Other way around, not going to work. So how do we get them to be maximized? Well, you could guess. You could try 30 degrees, 40 degrees, 50 degrees, and see what we get. Well, we just did it at 30 and got 19.88. Now let's try it at 40. Hey, I get a longer range. Hey, at 50 degrees, I get the same range. Oh yeah, they're complementary angles. Crank it up to 60, and you get 19.88 again. Hey, we can make a graph of range versus theta. At 0 degrees, we won't have any range at all. We'll be just at the ground, shooting it sideways. We launch at 90 degrees, we're going to go straight up, come straight down. We'll have no range again. And if we plot this data, we have some symmetry here, don't we? Starting to look like 45 degrees might give us the maximum range. Looks like we have a winner. Now you can try this at 44 or 46 degrees. You'll find out that the maximum is 22.96 meters at 45 degrees. Now I know you calculus fans know what to do with this. Take the derivative, set it equal to 0, but we can do something else. Combine the v's, rearrange, we've got this. Anybody smell a trig identity here? Yep, it's sine 2 theta. Now, how are you going to maximize the range? That's a constant. That's not going to change at all. Theta is the only thing you can change. So what's the biggest that sine 2 theta could ever be? Sine of any angle can't be bigger than 1. So 2 theta has to be 90 degrees, which means theta is 45 degrees. Now, you shouldn't just take my word for it. You want to build yourself a projectile motion launcher and test all of this. Here comes the next lab.